Welcome everyone to this simplified animated networking course. This course is designed for anyone struggling to understand networking concepts or looking to get started with computer networks. I guarantee that by the end of this course, you will have a solid foundation in computer networking with clear practical concepts. This course uses simple explanations combined with proper animations to explain networking concepts. Now, apart from all the essential topics in networking, I have also covered the binary number system, which is a bit advanced but equally important. Beginners often struggle with binary number system, but I have simplified it in a way that everyone will be able to understand it without any problem. My suggestion for you, especially if you are a complete beginner, is to avoid skipping any part of the video and learn sequentially. This way, you will be able to connect the dots and build a solid foundation as you progress through the course. This course is divided into two sections. In the first half of the course, we will cover all the essential networking concepts that form the foundation of networking, including important terms such as these. Then we will move on to the essential network devices used for creating a network. Moving forward, we will learn the most important topic, the OSI model in detail, which is the heart of computer networking, along with many other topics. In the second half, we will dive into advanced concepts that are particularly important for cybersecurity and ethical hacking. We will learn the essential cryptography and binary number system. If you want to learn more about networking and start your career in cybersecurity, you can check out my Udemy course. We will start by understanding the very basics, what a computer network is, why computer networks are needed, and what is resource sharing with real world examples. Don't worry about cables and devices used in creating a network. We will cover those details in upcoming sections. A computer network is essentially a group of interconnected computers or devices. When two or more devices connect to each other, they collectively form a computer network. The connection can be wired like this or wireless. Now, why do devices need to be interconnected? Because data can only be exchanged if devices are connected to each other. So when devices connect, they form a computer network. Once connected, they can start sending data to each other. That's why computer networks are required, because it enables devices to send data to each other. This is the simplest possible computer network. Later in the course, we will learn about more complex and sophisticated networks being used today. Computer networks were developed in the early 1960s, and back then only computers were part of a network. However, computing has evolved significantly. Today, a computer network is not limited to interconnected computers. Devices such as mobile phones, servers, tablets, switches, routers, printers, smartwatches, and other smart devices are all integral components of a computer network. Now let's address the real questions. Why are computer networks needed and what is resource sharing? As we have already discussed, devices can only exchange data when they are connected to each other. This forms a computer network enabling data communication. Apart from data communication, a computer network offers resource sharing, which is the most important feature or component of a computer network. Let's understand resource sharing with a few real-world examples. A network can be either wired or wireless. In a wireless network, devices connect to the network using Wi-Fi, right? When you connect to a Wi-Fi network, you and all other devices connected to that network can access the internet, right? This is an example of resource sharing where multiple devices connected to the same Wi-Fi network share or utilize the internet connection provided by the Wi-Fi network. Similarly, a computer network allows us to share devices like printers, scanners, servers, file servers, etc. Printers are essential devices in most offices, right? Now, without a network, each person or device would need their own printer, or they would all have to connect directly to the same printer. This is inconvenient, costly, and inefficient, right? Now, a network solves this problem by allowing devices on the network to share the printer. All we have to do is connect the printer to the network. Once you connect a printer to the network, then all the devices connected to the network can share or use the printer. They don't have to directly connect to the printer. Each device can use the printer whenever they need it. This is called the resource sharing that a network provides. Here I am showing you the printer being connected to a switch using a wire or Ethernet cable. However, printers can also connect to a wireless network or router. Nowadays, printers have wireless capabilities as well. Data sharing or file sharing is another common activity in offices and even in home networks. We can set up a file server where files can be stored and connect it to the network. Then everyone connected to the network can access the files. Otherwise, files would have to be sent to everyone individually, which can be time consuming. So guys, to summarize, a computer network allows devices to communicate with each other and share resources with other devices on the network. This saves money and makes it easier for people to work together. You will gain clarity on networks in the upcoming videos and sections. Now let's discuss types of networks. Computer networks are divided into different types based on their size and the geographic area that they cover. Some of the most common types of computer networks include LAN, MAN, WAN, WLAN, and personal area networks. In computer networking, the term packet is used all the time when dealing with data. A packet is a small segment of a larger file. When two devices exchange data over a computer network, such as the internet, the data or file is first divided into smaller pieces or segments called packets. The packets are then transmitted to the receiver. Let's understand packets with an example for better clarity. Let's say device A wants to send a file to another device B over the internet. Now, the file is not sent all at once. Before sending the file, it is divided into multiple smaller parts or segments, and these segments are technically called packets in computer networking. Then each packet is sent independently to its destination. At the destination, the packets are reassembled in the correct order to form the original file. So a packet is just a piece of a larger file and data is sent in a series of packets. Every web page, email, image, video or audio file that you send or download is transmitted in a series of different packets. At the destination, the packets are reassembled to form the original file. Now, why are files sent in this manner rather than all at once? Breaking a file into smaller packets improves data reliability. Let's say that if a packet is lost or corrupted during transmission, then only that specific packet needs to be resent. On the other hand, if you send a complete file all at once and it gets corrupted or lost in transit, the sender will need to resend the entire file. This would result in the waste of your bandwidth and network resources. Packets also improve efficiency. Dividing files into smaller packets allows each packet to take a different route to reach the destination. The maximum amount of data that a packet can carry depends on various factors such as the network technology being used and the specific protocol in use. The standard is currently 1500 bytes. The maximum size of data that can be sent in a single packet is 1500 bytes. There is a newer technology called jumbo frames. A jumbo frame can carry a maximum of 9000 bytes. We will discuss this further in the OSI model section in detail. Thank you very much, guys. IP address stands for Internet Protocol, and it is a unique number assigned to every device connected to a network or the Internet. When you connect to a Wi-Fi network or a wired Ethernet network, your device is automatically assigned an IP address. Now, why is an IP address needed? An IP address identifies each individual device on the internet. An IP address helps locate devices on the internet. IP addresses ensure that data reaches the correct destination. Just like individuals or businesses use a home or office address for sending and receiving mail, devices on the internet also needs a digital address for sending and receiving data. Let's say that you want to send an email or any type of data to someone in a different country or location. To deliver the data, the sender needs to know the location or address of the receiver. Then the sender will be able to deliver the data to that address or IP address. So this is what an IP address does. It essentially helps locate the device on the internet. Therefore, each device on the internet must have an IP address if it wants to access the internet or communicate with other devices on the internet. A device can send data to any other device anywhere in the world based on the IP address. Remember that computers communicate with each other using IP addresses on the internet. Without IP addresses, devices can't exchange data over the internet. Each packet contains two IP addresses: the IP address of the sender who is sending the packet and the IP address of the receiver where the packet will be delivered. There are two versions of IP addresses, IPv4 and IPv6. IPv4 is the most commonly used IP address. Now let me practically show you how to view your own IP address. Press Windows key, type CMD. Now click on command prompt and here type the command ipconfig/all. Press enter, and under the wireless LAN adapter Wi-Fi, locate the field that says IPv4 address. Here it is. As you can see, this is my own IPv4 address, and this is the IPv6 address. This is the IPv6 address, and if you are connected to your network using an Ethernet cable, then you will find all these network details under the Ethernet section. Let me scroll up. Here it is, Ethernet adapter, Ethernet. So if you are connected to your network using an Ethernet cable, then you will find the network details under this interface, Ethernet adapter. Host is one of the most commonly used terms in computer networking, so it is important to understand it at the beginning of the course. In networking, a host is any device that can communicate with other devices on a network. This means that any device that can send or receive data is called a host, such as computers, laptops, smartphones, tablets, servers, etc. Now we have new additions to hosts in modern days. These additions include smart devices such as smartwatches, smart refrigerators, gaming consoles, smart TVs, etc. These smart devices are capable of communicating or sending and receiving data. Each host or device capable of interacting with other devices has a unique IP address. This IP address enables seamless communication between devices on the internet. Whether you are a network administrator or have any role managing a network, dealing with servers will be a common task. So what exactly is a server? First of all, a server is also a computer. The name server might sound very intimidating, but it is essentially just another computer. So what makes a server different from a regular computer? The only difference between a regular computer and a server is that a server is configured to provide or serve specific services to users. The term server denotes a computer or program designed to serve or provide services to users or other computers. What a server serves depends on what you want it to serve. We have different types of servers. For example, a web server serves websites to users. In simple terms, a web server provides access to websites. When you type, let's say, cybersecurity on Google, it returns results related to your search query, right? Now, it is the web server that processes your request. Your search query is received by Google's web server, which then processes it and sends back search results to your web browser. As I mentioned earlier, a server is essentially just a computer. So how did Google turn a regular computer into a web server that answers your questions? To turn a regular computer into a web server, we need to install and configure certain things. First, we need to install software called a web server. There are two popular free web servers called Apache and Nginx, but Google uses its own server called Google Web Server, which processes your queries. Apart from installing a web server, we have to configure other aspects such as domain name, port forwarding, etc. to make a website accessible to everyone. By following these steps, you can effectively transform any regular system into a fully functional web server. There are many types of servers such as web servers, mail servers, file servers, database servers, DNS servers, etc. A web server delivers websites to users, a file server facilitates file sharing, and a mail server handles email communication. When you send or receive an email, it is the mail server that makes this process possible. Gmail is the most popular email service offered by Google, and it runs on its own dedicated mail servers. Typically, we use dedicated servers for each service. To summarize servers, whenever you install a service on a computer that serves multiple users, that computer becomes a server. Keep in mind that the servers need to be reliable, robust, and powerful because the server typically needs to be up and running 24/7. Let's say if Google's web server goes down, you will not be able to use Google. If Google's server goes offline even for a few minutes, it could cost them billions. Servers are usually accessible to many people and can be used for a variety of purposes. So let's start with the Ethernet cable. We can connect to a network in two ways, either through a wired connection or wirelessly, right? We connect to a wireless network using Wi-Fi to access the internet and other network resources. And if you want to connect to a wired network, you need a wire. Now, the wire or cable that makes this possible is called an Ethernet cable. An Ethernet cable connects computers to a wired network. Wired network is also known as an Ethernet network. The Ethernet cable is also known as the network cable. Here is what an Ethernet cable looks like. The Ethernet cable has a connector on each end. These are called RJ45 connectors. To connect a device to a wired network, we need to connect one end of the Ethernet cable to a computer and other end to a device such as a switch or router. Once connected, you will be successfully connected to the network and can access the internet or other network resources. Ethernet cables not only connects computers to a wired network, they can also be used to connect other devices like printers, servers, or any other device that supports it. This is just an overview of Ethernet cables. We'll get back to it in a dedicated section. Now let's move on to the LAN ports. Each system has one LAN port. This is what a LAN port looks like. To find the LAN port on your device, look for a small rectangular port that looks like this. Now, when you connect an Ethernet cable to a device, this is where the Ethernet cable gets plugged in. The RJ45 connector of the Ethernet cable gets plugged into the LAN port of a system. A LAN port is also known as the network port or Ethernet port. Routers, switches, computers, even printers have the LAN ports. You can also directly connect to computers using an Ethernet cable because it has connectors on both ends. Connect one end to one device and other end to the other device and you will be connected. Once connected, both devices can exchange data. So what is a MAC address? A MAC address is a 12-digit hexadecimal number. This is what a typical MAC address looks like. Later I will show you the actual MAC address practically. MAC stands for Media Access Control. It is also known as the physical address or hardware address. A MAC address is assigned to a network interface card. A MAC address uniquely identifies a computer. The MAC address is embedded or burned inside the network interface card. Each network interface card, whether wireless, wired, or external, has a unique MAC address embedded in it. A MAC address is permanent and can't be changed. MAC address is divided into two parts. The first 6 digits identify the manufacturer that developed the NIC and the remaining 6 digits identify the device itself. Now, let's address the actual question. Why is a MAC address needed? The MAC address is essential for data communication. If one device wants to send data to another device, it needs the MAC address of the receiver. In order for devices to exchange data on the same network or across different networks, they need MAC addresses of each other to exchange data between them. Here we have an obvious question. We also have IP addresses, right? What is the role of an IP address then, since the MAC address sounds similar to an IP address? Well, both MAC address and IP address work together to deliver data to the destination device. Remember, an IP address is not permanent. it keeps changing. Your ISP typically assigns a new IP address to your network or mobile phone automatically after a certain period of time. When you move to a new location or country, the internet service provider of that area also assigns you a new IP address. Therefore, we require a system that can pinpoint a device's location, and this is accomplished by the IP address. The main purpose of an IP address is to locate your current location. On the other hand, a MAC address is permanent and can't be changed. Therefore, we need both to communicate with other devices. The IP address is used to locate the device's current location after locating the device. The MAC address or physical address is used to deliver data to the actual physical device. Let's say there were no IP addresses. In this case, other devices or networks would assume that you are in the same location or network, even if you change your location or network, because MAC addresses are fixed. Therefore, we need IP addresses to differentiate devices based on their location, and an IP address gets updated based on your location. When you move to a new location, the ISP or internet service provider of that area automatically assigns a new IP address to your device. IP addresses are essential for sending data to devices in different networks or locations. An IP address locates the device, and the MAC address is used to deliver data to the physical device. Devices on the same network can communicate directly using their MAC addresses. We don't need IP addresses to communicate in the same network. Now let me practically demonstrate how to view your own MAC address. Press Windows key, type CMD, click on command prompt, and here type ipconfig /all, press enter, and under the wireless LAN adapter Wi-Fi, locate the field that says physical address. Here it is, physical address. This is how a MAC address looks like. This is my own MAC address for my wireless LAN adapter. As we have already discussed, the MAC address is also known as the physical address. Now, each network interface card has a unique MAC address. So this is the MAC address for my wireless LAN adapter, and let me find the MAC address for my Ethernet card. Let me scroll up. Here it is. As you can see, this is my wired Ethernet adapter, and this is the physical address or MAC address for my Ethernet adapter. To understand hubs, let's first discuss why hubs and similar devices are needed. This will provide the necessary context to understand hubs and switches. Suppose computer A wants to send data to B. To send data, first we need to connect these two computers directly with an Ethernet cable or by using a wireless connection. Once you connect them, it technically is a computer network. When two or more devices are connected to each other, it is called a computer network. Now, both connected devices can send data to each other. Obviously, it is the simplest possible network. This method of connecting devices directly to each other works well for two devices. However, if we add a third computer, we then need to connect it to both of the other computers for them to communicate with each other. If we continue adding more computers, we must connect each new computer to all of the existing computers. As the number of computers increases, connecting them all directly becomes increasingly difficult and inefficient. So wiring gets overwhelming. Now, hubs were developed to solve this exact problem. A hub was developed to simplify network connectivity. A hub simplifies how devices connect to each other and communicate efficiently with minimal wiring. A hub is a central multi-port device with multiple ports where various devices can connect. To connect a system to the hub, an Ethernet cable is required. An Ethernet cable has connectors at both ends called RJ45 connectors, right? To connect your computer or any device to a hub, connect one end of an Ethernet cable to the system and other end to the hub's LAN port. Similarly, other devices can connect to the hub using Ethernet cables. Once you connect your system to a hub, you can communicate with all the devices that are connected to the hub. Now, your computer is part of this LAN network. A LAN network can be created using a hub. When multiple devices connect to a hub, they collectively form a computer network. This is a LAN network. These connected devices can send data to each other through the hub. The hub manages communication between all the connected devices. Now let's understand how a hub facilitates communication between devices. The way a hub works is that when it receives a packet, it sends that packet to all the devices connected to it. Let's say that A wants to send data to C. The packet first goes to the hub and the hub broadcasts or sends the packet to all devices connected to it, including the destination device C. The hub basically copies the packet to all its ports. However, by default, all other devices reject or discard the packet except for the intended device C. Only the destination device C accepts the packet. Each packet contains the MAC addresses of the sender and receiver. When the packet arrives at device C, it checks the destination MAC address in the packet to see if it matches its own MAC address. If the MAC addresses match, then device C accepts the packet because it is intended for it. So that's how a hub works. Each packet that arrives at the hub is sent to all the connected devices. However, only the device for which the packet is intended accepts it, while others reject it. Similarly, all other devices connected to the hub can send data to any device that is connected to it. The communication flow remains the same. The packet that one system sends to a specific system connected to the hub is sent to all other devices connected to it. This is a drawback of a hub. We will discuss it in the next video. So guys, that's how a hub simplifies connectivity. You only need an Ethernet cable to connect to the network or hub, and then you can communicate with all other devices connected to it without having to connect to them directly. A switch is essentially an improved version of a hub. It is an advanced networking device that addresses the limitations of hubs. It offers significant improvements in network performance, security, and efficiency. A hub has two major flaws. It lacks intelligence and is insecure. When a hub receives a packet, it forwards it to all connected devices, even if the packet is not intended for them, leading to unnecessary data exposure and potential security risks. This creates a security concern because by default, devices connected to a hub only accept or receive the packet that are sent to them. However, a computer or network card can be configured to accept packets that are not sent to it. Now, this modification makes the network less secure because devices can potentially receive and process data packets that are not sent to them, and they could potentially intercept and steal sensitive data being exchanged between other devices. Another drawback of a hub is that it generates unnecessary network traffic because instead of sending packets directly to the intended receiver, a hub sends all packets to all connected devices. This can lead to bandwidth congestion and slow down the network for all users. Now, the switch basically addresses these two problems or limitations of a hub. The switch is similar to a hub. This is how a switch looks like. A switch is also a multi-port central device with many LAN ports. The total number of ports in a switch depends on the size and type of switch. Most switches have a minimum of 5 LAN ports, and there are switches with 12, 24 and 48 ports as well. The switch allows computers or other devices to connect to a network through an Ethernet cable, so that they can communicate with each other and access the internet and network resources. The process of connecting a device to a switch is the same as we discussed in the previous video. We have to connect one end of the Ethernet cable to the computer and other end of the Ethernet cable to the switch. We can connect computers, servers or printers to a switch using an Ethernet cable, which allows them to communicate with each other. Once you connect devices to a switch, it creates a LAN or local area network. A simple LAN can be created using a switch by connecting devices to it. Unlike a hub, a switch is a smart device. The way a switch works is that it stores the MAC address of each device connected to it. A switch basically learns which device is connected to which port by maintaining a MAC address table. The MAC address table stores the MAC address of each device connected to the switch and the port number on which the device is connected. For example, if device A connects to port 1 on the switch stores its MAC address in its MAC address table along with the port number to which it is connected. This is how the entry looks like in the table. This means that computer A is connected to port number 1. The switch does this for every device that connects to it. It stores the MAC address of each device and the port number to which they are connected. And how a switch exactly acquires the MAC addresses will be covered in a separate video. Now let's see how a switch works and forwards data. Let's say device A wants to send data to C. The packet first goes to the switch. Every packet contains two MAC addresses, the MAC address of the sender and the MAC address of the receiver or destination where the packet needs to be delivered. Now the switch checks the destination MAC address in the packet and matches it against the addresses in the MAC address table. If the destination MAC address is found in the table, then the switch forwards the packet to the port number associated with that MAC address. In this case, the destination MAC address is at port number 3, so the switch forwards the packet to the device C. So unlike a hub, it sends packets only to the intended device. Similarly, if any device connected to the switch wants to communicate with another device, the same process is followed. The packet goes to the switch checks the MAC address table and forwards the packet to the destination. A switch is capable of reading MAC addresses, whereas the hub can't read MAC addresses. That's why it forwards packets to everyone. So guys, that's how a switch works. The data is delivered or forwarded only to the intended device, making it secure. A switch is among the most commonly used devices today. In wired network, a switch is always the preferred device. We are continuing where we left off in the previous video. In this video, we will discuss routers. Routers are extremely important. Now, to understand routers, let's first review the central devices we have already covered, such as hubs and switches. This will help us understand routers more clearly and provide the context for understanding routers and their requirements. A hub or switch allows devices to communicate with each other within the same network or local area network, right? The devices connected to a switch can communicate with each other easily. Now let's say that device A wants to access Google or the internet. However, Google server is not available within the network or LAN. It is located somewhere on the internet. Therefore, to access google.com or the internet, computer A and all other devices in the network must leave their own network to reach or access Google. A switch can't route or send data outside of the network. It is designed to facilitate communication only within the same network or LAN. So we need a device that can route or send data packets outside of the local area network. That device is a router. A router allows devices on LAN networks to communicate with external networks such as the internet. This is how a router looks like. So to access the internet, we must connect the switch to a router and the Ethernet cable is used for this connection. Just connect one end of the Ethernet cable to any LAN port of the switch and other end of the cable to the LAN port on the router. A router has at least one LAN port. Once the switch is connected to the router will connect your network to the internet. Now, devices connected to the switch or network can access the internet. Now, when any device on the LAN network needs to access anything on the internet, the switch forwards packets to the router and the router sends the packets to the destination. A switch understands MAC addresses, which means it forwards packets based on the destination MAC address. On the other hand, a router understands IP addresses. A router forwards packets based on the destination IP address in the packet. Now let's understand the complete communication flow with an example. Let's say device A wants to access Google. The packet first goes to the switch and then the switch forwards the packet to the router. As mentioned earlier, routers work with IP addresses. The router checks the destination IP address in the packet. In my case, the packet contains IP address of Google, and based on this destination IP address, the router forwards the packet to the Google, and the reply that Google sends back to device A will follow the reverse path like this. Packet arrives at the router, which forwards it to the switch, and the switch forwards it to the destination device A. Similarly, if any other device connected to the switch or wirelessly wants to access the internet, communication process remains the same. Remember that most routers also have a built-in switch. You can directly connect computers to a router using an Ethernet cable. However, a router typically doesn't have many LAN ports, so a dedicated switch is typically used for wired connectivity and provides connections to more devices. So if you are directly connecting to the router, it means the router has a built-in switch. Another very important function of a router is to select the path that packets need to take to reach their destination and then forward them. The internet is essentially a huge collection of interconnected networks or LAN networks. This means that different networks communicate with each other to forward data to the correct destination. The networks communicate with each other through routers. Routers connect the networks. Therefore, each network must have a router if it wants to access the internet. Since the internet is a web of interconnected routers, data must go through these routers to reach its destination. The job of a router is to select the best available path that packets need to go through to reach their destination. This is called routing. Routing is the process of selecting the path that data must go through to reach its destination. There are two main types of routers: wireless routers and wired routers. A wireless router allows devices to connect to a network wirelessly using Wi-Fi. A wireless router is used to create a WLAN, wireless local area network. On the other hand, a wired router allows devices to connect to the router using a wire or an Ethernet cable. These routers are mostly used in home networks and small offices. Keep in mind that a wireless router typically supports both wired and wireless connectivity. A wireless router may or may not have multiple LAN ports. However, each wireless router has at least one LAN port. So far, we have learned about fundamental network devices like switches, routers, and Ethernet cables. Now, the only missing mandatory component needed to create a functioning network is a modem. So in this video, we will learn what a modem is, how it works, and the difference between a modem and a router. So let's first understand what a modem is and why it is needed. The modem, in simplest terms, brings the internet to your home or office. It essentially connects your LAN network to the internet. Suppose you decide to set up a broadband internet connection at your home or office. In this case, you will first need to contact your local internet service provider and purchase a broadband connection from them. To provide internet access to your location, your ISP will use a cable or wire to connect your home to the ISP's network. To deliver the internet, a modem essentially maintains a dedicated physical connection from your home or office to your internet service provider. The cable provided by your ISP is plugged into the modem. Now, modem needs to be connected to the router. The cable used for connecting the modem to the router is an Ethernet cable. Connect one end of the Ethernet cable to the LAN port on the modem and the other end to the WAN port on the router. I am repeating again, connect the other end of the Ethernet cable to the WAN port on the router. There are two types of ports on routers: LAN and WAN. The WAN port essentially connects your network to the internet. You might also see internet instead of WAN port. They are both the same thing. Once you connect your router to the modem using the WAN port, you will be able to access the internet. Most routers have several LAN ports, typically around 3. You can connect your computers to these ports and access the internet. If you need more Ethernet ports for wired devices, you can connect a switch to your router as we discussed in the previous video. Routers can be either wireless or wired. If your router is wireless, devices on your network can access the internet using Wi-Fi. Now you have a functioning network. Now let's discuss some of the technical details and main functions of a modem. A modem converts analog signals to digital signals and digital signals to analog signals. This conversion is absolutely necessary because the wires or physical cable infrastructure that brings the internet to homes and offices use analog signals. The data is transmitted in analog form through the wires. However, computers and other digital devices only understand binary language or digital signals, zeros and ones. So we need a device that can convert analog signals to digital signals and vice versa. The modem is that device. Modem stands for modulator demodulator. Modulation is the process of converting digital signals to analog signals, and demodulation is the process of converting analog signals back to digital signals. When the analog signals arrive at the modem, it converts them back to digital signals so that computers and other digital devices can understand or read them. The modem can be a dedicated device, but now they are often built into routers. These days, a router has a built-in modem. This means that you can have a router that also functions as a modem. However, there are still some cases where you might need a dedicated modem, such as if you have a very high-speed internet connection or a complex network setup. Now, the modem seems to be very similar to the router, right? However, there is a difference. A modem is a device that connects your home or office to your internet service provider through a physical connection or wire. It brings the internet physically to your place. On the other hand, a router allows devices connected to the network to access the internet. As we discussed in the previous video, routers also decide the path that packets must pass through to reach the destination. We are going to wrap up this section with wireless access points. It is another important device used in computer networks. So in this video, we will learn about the wireless access point and the difference between a wireless access point and a router. Sometimes people mistake both devices for being the same. A wireless access point is also known as a wireless AP. This is what a wireless access point typically looks like. It typically has external antennas. However, some access points have built-in antennas as well. Now, before we discuss the wireless access point in detail, let's talk about routers briefly. Then we will be able to understand why wireless access point was developed. There are two types of routers, wireless routers and wired routers. A wireless router supports wireless connections, allowing different devices to connect to the network wirelessly using Wi-Fi. On the other hand, the wired router does not support wireless connectivity. You can't connect to a wired network or router using Wi-Fi. We have to use the Ethernet cable to connect to a wired router. Now let's say that you have a wired router that does not support wireless connectivity, and you want to enable wireless connectivity so that devices can connect to the network wirelessly using Wi-Fi. This is where the wireless access point comes in to solve the issue. A wireless access point is a network device that allows devices to connect to a network using Wi-Fi or wirelessly. Now, to enable wireless connectivity, we need an Ethernet cable. Simply connect one end of an Ethernet cable to the wireless access point and the other end to the wired router. The wireless access point can also be connected to a switch as well. Now it will start transmitting the radio waves. Now devices such as computers, mobile phones or tablets can connect to the network wirelessly using Wi-Fi. So an access point is a device that allows wireless devices to connect to a wired network. A wireless access point can also be used to extend the range of a wireless network. Wireless access points are frequently used in homes, businesses, and other public places to extend the reach of a Wi-Fi network and offer improved coverage. Let's say if you have a large office with multiple blocks and many people, a wireless router has limited range and it can't provide connectivity to everyone in the large block. This is where we can use the wireless access point. You can add one or more wireless access points to extend the Wi-Fi signal to all areas of your office or home. To do this, you simply need to connect the wireless access point to the main router using an Ethernet cable. Once the access point is connected to the main router, it will provide access to the wireless network. Now, devices from all corners can access the network using their Wi-Fi. All the devices are connected to a single network using different access points. This entire network is managed by the main router. If any device on the network wants to access the internet, the packets have to go through the main router. Everything is managed by a single router. Wireless access points are well suited for such setups or large offices because they are easy to manage. Alternatively, you can also use wireless routers instead of wireless access points to provide wireless connectivity to everyone by placing individual wireless routers instead of wireless access points. However, this can create manageability problems. For example, if you use wireless routers instead of wireless access points, you will need to configure each router individually if you want to make changes to the network. However, with wireless access points, you can manage the entire network using a single router. This is because wireless access points are typically connected to a central router, which allows you to configure all the APs from a single location or device. Now let's talk about difference between a wireless router and wireless access point. Wireless routers and wireless access points are two different devices with distinct capabilities. A wireless router can support both wired and wireless connections. Typically, a router has multiple features such as a built-in switch, firewall, DHCP server, etc. A router supports all these features. On the other hand, the sole purpose of a wireless access point is to provide wireless connectivity and extend the network coverage. It only transmits radio waves so that devices can connect to the network wirelessly. That's all you need to know about the wireless access point. The OSI model is one of the most important topics in computer networking. The OSI model is the foundation for understanding network architecture. Alright, so what is the OSI model? OSI stands for Open Systems Interconnection. In simple terms, if you want to understand how two devices sitting in different countries or on the same network are able to communicate and send data to each other, then the OSI model is your answer. The OSI model basically explains each component involved in sending and delivering data from one computer to another over the internet. such as how data is prepared before it leaves the sender's computer, how it travels through various paths or networks to reach the destination, and finally how data is processed and received by the destination device or receiver. Sending data from one device to another over the internet is a very complex process that involves many steps. Let's say you want to send a file to someone who is sitting in another country or network. Your system has to figure out where to exactly send the data, how to send it, and make sure that the data is delivered to the receiver without any errors, etc. So the OSI model helps us to understand all of these steps involved in the process of sending and receiving data over internet in detail. That's why OSI is essential in computer networking. As a network administrator or cybersecurity engineer, learning the data communication process is the most fundamental thing. The OSI model is a 7-layer model. Transmitting data over the internet is a complex task. To simplify this problem, OSI divided all the functions into 7 smaller parts. In technical terms, these parts are called layers, OSI layers. Each layer of the OSI model is assigned specific tasks or responsibilities. The reason for splitting the OSI model into 7 layers is simple. It makes it easier to detect and solve problems separately. This layered approach can easily tell us in which part the error or problem is. All 7 layers work together to transmit data from one device to another across the globe. The OSI model is very useful for troubleshooting network problems. Network engineers always use the OSI model to detect and troubleshoot network problems. Once you understand the function of each layer, it helps us pinpoint errors to specific layers. Using OSI, we can narrow down and isolate the errors or possible causes of the errors to a specific layer and resolve it more quickly and easily. The layered approach works best for troubleshooting. The first layer in the OSI stack is the application layer. The layers in OSI are numbered from bottom to up. The application layer is the 7th and the first layer from the top. Now the application layer is closest to us, the end users. Application layer allows us to access or use different network services such as sending emails, making video and audio calls, transferring files, browsing websites, etc. We access or use these network services using various network applications. Network applications are those that depend on the internet for communication, such as Zoom for video calls, web browsers like Chrome or Firefox for browsing websites, Outlook for emails, and FTP clients for file transfers, etc. All of these are network applications. Now, to be very clear, network applications are not part of the application layer. They don't reside within the application layer. Network applications depend on the application layer to function properly. The job of the application layer is to provide the protocols that various network applications need to function correctly. The application layer communicates or interacts with network applications through its protocols. Each layer of the OSI model has its own set of protocols. The application layer has many protocols such as HTTP, HTTPS, Telnet, SIP, SSH, FTP, etc. Network applications depend on these protocols to function correctly. Let's understand this with a few examples. When you browse a website, it is the HTTP protocol that makes the web surfing possible, allowing you to view websites. At the beginning of each URL, you will see either HTTPS or HTTP, right? All web applications depend on the HTTP or HTTPS protocol to function properly. HTTPS is essentially the secure version of HTTP. That's why you see HTTPS at the beginning of most website URLs. Both protocols are part of the application layer. When you visit a website, your network application such as Firefox interacts with application layer using the HTTP protocol. If you send or receive an email, it is done using the SMTP protocol. SMTP protocol manages emails. File transfer is done through FTP protocol. Video calling applications like Zoom or Discord use the SIP protocol along with other protocols. SMTP, SIP, SSH and FTP, all these protocols are part of the application layer. Therefore, all network applications or services rely on application layer protocols to function correctly. So to summarize, the application layer provides the required interface and protocols for network applications to function. Each layer of the OSI model coordinates with specific devices. The OSI model is all about explaining data communication process, and in computer networking, it is the actual physical devices that make data communication possible, right? Therefore, each layer of the OSI model coordinates with specific devices. And the application layer devices are those that we use to access network applications or generate data, such as personal computers, mobile phones, laptops, tablets, etc. We run networking applications on these devices to access websites, make calls, and transfer files, etc. So these devices operate at the application layer. Servers are also application layer devices. The data or protocol data unit at the application layer is simply called data. We will learn more about it in later video. The presentation layer receives data from the application layer. The presentation layer performs four main tasks: translation, encryption, decryption, and compression. Let's discuss them one by one, starting with translation. The presentation layer receives data from the application layer in its raw form. It can be characters, numbers, images, or any other data generated by users through network applications. Therefore, it translates or converts the data into a format that a machine can understand, which is binary, ones and zeros. The raw data gets converted or translated into binary. Presentation layer is also responsible for translating data into a syntax or format that the application layer of the receiving device can understand. The two devices that are communicating might use different encoding methods. Encoding in computers is the process of converting data such as text, images, audio, or any digital data into a format that can be stored or transmitted electronically. For example, when you press, let's say, the key A on your keyboard, A is converted into a binary code using an encoding scheme like ASCII. The data can only be stored or transmitted after it is encoded. This binary code is then stored in the computer's memory or transmitted over a network. Similarly, all types of data such as audio, video, and images are converted into binary. Encoding is a separate topic that will be covered in a dedicated section. There are different encoding schemes such as ASCII and EBCDIC. Let's say the sender uses the ASCII scheme for encoding data and the receiver is using the EBCDIC method or scheme. Then the presentation layer converts ASCII to EBCDIC so that the receiving device can understand the data and display accurately. Without converting one format to another, data will not be displayed or represented accurately by the receiver. Encoding is a vast topic beyond the scope of this video or section. Just understand that if needed, the presentation layer can convert one encoding scheme to another. This is called translation in the presentation layer. Another important responsibility of the presentation layer is encryption and decryption. When two devices are communicating over an encrypted connection, the presentation layer handles encryption and decryption. Encryption is used to protect your data from cybercriminals. HTTPS websites are examples of encryption. When you visit an HTTPS website, your data is encrypted before it leaves your system. Encryption is simply the process of making data unreadable before sending it to the destination. Now, if a hacker or cybercriminal intercepts the data or your communication, they can't see what you are sending or receiving. They will only see the encrypted text. Only the receiver can see the original data because the data is decrypted back to its original form only at the receiver's device. Only the receiver can decrypt the data. All the big applications and websites use encryption to protect your data. Like I mentioned earlier, in the application layer, each layer has its own set of protocols that manage different things. In the presentation layer, we have the TLS protocol, which is responsible for encrypting and decrypting data. So encryption, decryption, and data security are handled by the presentation layer. The presentation layer is also responsible for data compression, which is a method used to reduce file size. It achieves this by reducing the number of bits that represent the original data. It uses compression algorithms or techniques to reduce the size of files so they can be transmitted more quickly. Compressing data does not impact the file itself. It merely reduces the file size and the receiver will receive the complete file. These are the protocols at the presentation layer. The session layer receives data from the presentation layer. It is responsible for managing sessions, authentication, authorization, and creating checkpoints. Let's first discuss the session management. The session layer controls the sessions between devices that are communicating or exchanging data. A session is essentially the period of time when two devices start their communication and when they stop communicating or end their communication. The session layer is responsible for creating, maintaining, and terminating sessions. It maintains session between communicating devices. Your computer can communicate with multiple websites or servers simultaneously, right? You might be logged in to Amazon at the same time. You can be browsing other websites such as YouTube, Wikipedia, etc. To manage this effectively, the session layer creates a unique session for each server or device that your device is communicating with. It assigns a unique ID to identify each session. It maintains separate sessions for each device and keeps track of which data belongs to which session or server. The session layer keeps the session open until both devices finish their data exchange. When you log out of website or exit the web browser, the session layer terminates the session. That's the session management. Now let's discuss authentication. Authentication is the process of verifying the identity of a user. It is typically performed by the server. Let's understand authentication with real-world examples. Suppose you want to log in to your Amazon account. Before logging in, you must verify your identity by providing your username and password, right? After submitting your login credentials, Amazon authenticates or verifies your credentials and allows you to log in if they are correct. This is an example of authentication in the real world performed by the session layer. When authentication is successful, the session layer creates a new session. The session is typically created after the server successfully authenticates the user's login credentials. A session represents the period during which a user stays logged into a system or application, and the session is terminated when the user logs out of the application. Now let's move to the authorization. Authorization is the process of determining what users are allowed to do after they have been authenticated or logged in. For example, after you log in to your Amazon account, you are authorized to browse and purchase items. However, you are not authorized to change the price of items. Authorization determines what actions a user is permitted or not permitted to perform. Now the next important function of the session layer is creating checkpoints. A checkpoint is also known as session restoration. Checkpoints are a way to save the current state of a session so that it can be resumed later even if session is interrupted. When a session is terminated abruptly, it preserves the session as it was at the time of disconnection or interruption. Let's understand this with examples. You may have noticed that when you download a file using download managers like IDM or FDM from the internet and your internet connection is abruptly disconnected or disrupted, and when you reconnect to the internet again, the download resumes from the exact point where it was interrupted. It does not start downloading from zero, or you can also pause the download and resume it later. This is because the session layer keeps track of what has been downloaded by establishing checkpoints. In the event of a sudden disconnection or pausing the download, these checkpoints help resume the session from the last point where the disruption occurred. Another example that you have likely experienced is when your web browser crashes or shuts down suddenly, and when you open it again, you may see a restore button, right? Clicking on this button will reopen all the tabs that you had opened prior to the browser's abrupt shutdown. This is also an example of session restoration or checkpoints. The transport layer receives data from the session layer. The functions of the transport layer include segmentation, flow control, error control, process-to-process delivery, and reliable and unreliable data delivery. The transport layer will be covered in two videos. This is the first part where we will discuss segmentation and process-to-process delivery. Let's start with the segmentation first. Segmentation simply means dividing data or a file into smaller parts. These parts are called segments in technical terms. That's why the protocol data unit or data at the transport layer is called segment. Now, why a file needs to be segmented? Well, computers don't send complete files all at once. Let's say that A wants to send a file to B. Now, the file is not sent all at once. Instead, it is first divided into smaller segments, and then each segment is sent independently to the receiver. Let's understand how segments are created. The transport layer receives data from the session layer in the raw form of continuous binaries, ones and zeros. Now the transport layer takes the bits and converts them into bytes. The transport layer deals with data in the form of bytes. After converting bits into bytes, the bytes are then put into segments. Each segment is a collection of bytes. Each segment contains a specific number of bytes. The bytes are numbered sequentially within each segment. Each byte has a unique sequence number assigned to it. The sequence numbers help to reassemble data packets or segments in the correct order, even if segments arrive out of the order at the destination. For the sake of simplicity, let's assume segment 1 contains 5 bytes and your sequence numbering starts from 2001. Your operating system selects a random number for the first byte and then increments the number by 1 for each subsequent byte. So the sequence number for the first byte is 2001, for the second it is 2002, and so on until the last byte in the segment, which is 2005. In the second segment, the sequence numbering continues from where the last segment ended. Therefore, the first byte will have the sequence number 2006, the second 2007, and so on until the last byte in the segment, which is 2010. This is how sequence numbers are assigned for each segment. If there is a third segment, its sequence number will start from 2001 because the previous segment ended at 2010. Now these sequence numbers help to reassemble the data in the correct order to form the complete file. Each segment is sent independently to the destination and then reassembled in the correct order to form the original file. So to sum up, the segmentation in transport layer takes the data or a file, then breaks it into many segments, and then each segment is sent separately to the receiver. Segments are transmitted over the internet to their destination by another protocol called IP in the form of packets. Now next important responsibility of the transport layer is process-to-process delivery. This is also called end-to-end or port-to-port delivery. Okay, let's break this down. Process-to-process delivery helps devices deliver data to the correct processes. A computer typically runs multiple processes simultaneously, right? A process simply refers to an application program that is running. In technical terms, when you execute or start a program, it becomes a process. For example, when you start Firefox, it becomes a process named Firefox while it runs. Now think about it. You can browse multiple websites in different tabs, make video or audio calls, and send emails at the same time from a single device, right? When you have multiple applications or processes running, how does the system determine which process to send data to? When a system receives data, how does it know to which process the data needs to be delivered, which process the data belongs to? So computers need a way to identify each running process so that data can be delivered to the correct process. To achieve this, computers use something called port numbers. Port numbers identify each running process on a system and help deliver or forward data to the correct process. The operating system assigns a unique port number to each running process or network service. So after creating segments, the transport layer adds the source and destination port numbers to each segment. Source port refers to the port number of the sender's device and destination port refers to the port number of the receiver or destination's device. There are a total of 65,535 port numbers. However, the first 1023 port numbers have specific or predefined rules. These ports are reserved for well-known services such as websites, email, file transfer, etc. For example, port number 80 is always used for HTTP traffic or websites, and port number 443 is the default port for HTTPS traffic, which is a secure version of HTTP. Suppose you visit an HTTPS website. When the request or packet reaches the destination server, the request is forwarded to port number 443 because port number 443 processes HTTPS traffic. Port number 687 is reserved for emails, where it processes the email data. Now let's understand the entire process-to-process delivery with real-world examples to gain more clarity. Let's say you want to access google.com. As I mentioned earlier, the transport layer adds two port numbers to each segment, the source port and the destination port numbers. The operating system selects a random port number for the source port. Let's say 1111. Source port means the port number of the sender's device. However, the destination port number will be 443 because the device is attempting to access Google. Google uses HTTPS and port number 443 processes the HTTPS requests. And the default port for HTTPS is 443. Now, when the packet reaches the destination at Google's server, there are obviously multiple processes running on the server. The server checks the destination port number in the segment, which is 443. So, it forwards the segment to the process or port number 443, where a program called a web server processes the request. Now, Google sends back the reply to A. Before sending the reply, Google swaps the port numbers. This time Google is the sender, so the source port number will be 443 and the destination port number will be 1111. Now, when the segment reaches destination A, it checks the destination port number, which is 1111, and sends the segment or data to the intended port or process associated with that port. Now, let's say that device A accesses another website called YouTube in a new tab. Then the operating system will generate a new random port number for the new tab or website. Let's say the port number is 2222. So the source or sender port number is 2222 and destination port number is 443. When the YouTube sends a reply back to A checks the destination port number, which is 2022 this time, and then forward it to the process or tab associated with the port number, which is 2022, and the data or segment finally gets displayed in the tab. And when you open a new tab or launch another process like Zoom, the operating system assigns a unique port number to each process. Each tab and process has its own unique port number acting as a unique identifier. That's how data is directed to the correct process by computers. Now let's move on to the flow control. Flow control at the transport layer is a mechanism used to control and manage the flow of data between two communicating devices. Flow control determines the amount of data that needs to be transmitted or sent to the receiver. If the sender sends more data than the receiver can handle or process, then the data will be lost and wasted. Flow control makes sure that the sender does not send more data than the receiver can handle or process. Let's take an example. Suppose you are downloading a file from the internet. The server from which you are downloading the file can transfer data at 100 Mbps rate, but your network has a slow internet connection and can only process or accept data at 5 Mbps speed. Now, if the server starts sending data at a rate of 100 Mbps, which is significantly faster than your network's processing capacity, the data will obviously be lost and wasted. This is because your device can't process or receive data beyond its current speed of 5 Mbps. Now the transport layer controls the data flow, how much data should be transmitted to the receiver. Before sending data, transport layer asks the receiver how much data it can process. The receiver then informs the sender about its receiving capacity. The receiver advertises or tells how much data it can process. The sender then sends the data at the rate that the receiver has advertised or informed the sender. Flow control is managed through window size. You will learn more about it in the TCP section. This is a basic overview. Another important function of the transport layer is error control. The transport layer makes sure that error-free data is delivered to the receiver. If the data becomes corrupted or does not reach the destination, or someone modifies the data before it reaches the destination, then it is the responsibility of the transport layer to resend the corrupted or lost data segments. It uses the automatic repeat request algorithm to retransmit the lost or corrupted data. The transport layer adds a checksum to each segment to ensure that error-free data is delivered to its destination. The checksum essentially checks for any edits or modifications in the data. If the data is modified after leaving the sender's device, the transport layer checks for data modifications at the receiver's device to ensure that the data was not altered or modified. If it is found to be modified, it is dropped. Now let's discuss reliable and unreliable data delivery. The transport layer provides both reliable and unreliable data delivery depending on the needs of the application. We have two major protocols at the transport layer, TCP and UDP. We also have SCTP, but UDP and TCP are the most commonly used and dominant protocols. TCP and UDP are used for different types of applications. TCP protocol provides reliable data delivery, meaning that it guarantees that the data will be delivered to the receiver in the correct order and without any errors. On the other hand, UDP provides unreliable data delivery, meaning that it does not guarantee that the data will be delivered to the receiver. Now, most applications need to receive all of the data in the correct order without any missing parts. TCP ensures that this happens. The transport layer uses TCP protocol for applications where guaranteed data delivery is mandatory, such as emails, chat systems, web browsing, and file downloading, etc. For example, when you download a file from the internet, the transport layer uses TCP to ensure that the entire file is downloaded correctly without any missing parts. Similarly, the transport layer uses TCP for other applications such as emails, web browsing, etc. TCP is a connection-oriented protocol because in order to guarantee data delivery, TCP establishes a connection between the sender and receiver before exchanging the data. Now let's talk about unreliable data delivery. The transport layer uses the UDP protocol when guaranteed data delivery is not a priority. Some applications such as live streaming, VoIP audio or video calling, and online gaming don't care about the guaranteed data delivery. For example, if you are watching a live stream and your internet connection stops or you get disconnected for a few seconds, when you reconnect, the stream will not resume from where you left off. Instead, it will only show you the current live content. The packets that were lost during internet disruptions are not retransmitted in this case, because if the lost packets were retransmitted, then it would no longer be a live stream. UDP keeps sending data regardless of whether it reaches its destination or not. UDP is fast. It is a connectionless protocol, meaning that it does not establish a connection with the receiver like TCP does. The transport and all other layers of the OSI model relies on protocols to complete tasks. Each layer has its own set of protocols. Everything is done using the protocols. These are the devices and protocols at the transport layer. As you learn more, you will start connecting concepts or dots and making sense of them. This is just the beginning. The network layer receives data from the transport layer. The major responsibilities of the network layer include host-to-host delivery, logical addressing, routing, and fragmentation. Now let's discuss them one by one, starting with host-to-host delivery. Host-to-host delivery means taking data from the sender's device and delivering it to the receiver. The transport layer creates segments, right? Now these segments need to be delivered to the destination. The transport layer can't do that. It only creates segments. Someone needs to deliver these segments to the receiver. This is exactly what the network layer or host-to-host delivery does. It takes segments from the transport layer and deliver each segment as a packet to the receiver's device or another host in a different network. The data is called packet at the network layer. This is also called source to destination delivery. After delivering the data to the receiver, the network layer passes the data to the transport layer. The transport layer then delivers the data to the exact process or application that requested it. This process is called process-to-process delivery, as we discussed in the transport layer. Process-to-process delivery only happens after the data reaches the destination device. The job of network layer is to deliver data to the destination, and then the transport layer delivers data to the exact process. This is how both layers work together. Remember, data moves from bottom to up on the receiver's device. Now let's discuss logical addressing. Logical addressing is the process of assigning source and destination IP addresses to data segments. The network layer receives data segments from the transport layer and then adds the source and destination IP addresses to each segment to form packets. The PDU or data is called packet at the network layer. The network layer adds the IP address of the sender, the device sending the packet, and the IP address of the destination device where the packet will be delivered. Each device that is connected to the internet has a unique IP address. An IP address uniquely identifies a device on the internet. The IP address essentially determines where the device is located on the internet. To deliver data, the sender needs to know the destination address. Therefore, the network layer adds the destination IP address to each packet. Then the packet gets delivered to the destination IP address or device. The network layer also adds the source IP address or the sender's IP, because when the receiver sends the data back to the sender, it also needs to know where the packet should be delivered. That's why the source and IP addresses are added to the packets. So to summarize, IP addresses are added to data so that packets can reach the correct destination. That's the logical addressing. Now let's move on to routing. Routing is an important function of the network layer. Routing is the process of selecting the best possible path to deliver data to the destination. The internet is essentially a huge collection of different individual networks or LAN networks. All the LAN networks are interconnected. These interconnected individual networks form the internet. Now remember that networks communicate with each other through routers. Routers communicate with each other to direct or forward data packets to the correct destination. Packets have to travel through various routers to reach their destination. There is never a direct or dedicated link between the sender and receiver. Data has to go through various networks or routers to reach its destination on the internet. Let's understand this with an example. Suppose device A wants to send data to B over the internet. Both are located in different networks. Now, data does not travel directly from the source to the destination. As discussed earlier, it has to pass through various routers to reach its destination. So here we have a lot of possible routes. Now the sender has to select the best possible route to deliver data. The job of the routing is to select the best possible route among all the available routes to deliver the data to the destination as quickly as possible. In our example, routing has selected these three routers that data needs to pass through to reach the destination. This is important. These routers that the data goes through are also known as nodes or hops. The network layer uses various routing protocols to determine the path, such as EIGRP, BGP, and RIP, Routing Information Protocol. Now let's discuss fragmentation. Fragmentation is another important responsibility of the network layer. Fragmentation simply means breaking a packet into smaller pieces or fragments. Now, why do packets need to be fragmented? The transport layer also breaks a file into smaller pieces or segments, right? Which is called segmentation. But there is a difference. Segmentation means breaking a file into smaller pieces or segments at the transport layer, and fragmentation means breaking a segment or packet into smaller pieces at the network layer. The fragmentation is required in certain cases because a single packet can carry a maximum of 1500 bytes. However, there is a new technology called jumbo frames that can carry up to 9000 bytes in a single packet. The jumbo frames are mostly used by data centers for now. They are not common at all. A single packet can carry a maximum of 1500 bytes, which is the current standard. This is also called MTU, Maximum Transmission Unit. MTU defines the total data that can be transmitted or sent in a single packet. Now, each network has its own MTU or capacity to handle data in a single packet. Let's say the sender sends a packet of 1400 bytes to the receiver, but the receiver's network has an MTU of 700 bytes. The receiver's network only accepts a maximum of 700 bytes in a single packet. The receiver will not be able to process or handle a packet with 1400 bytes because its MTU is 700 bytes. Now the sender has to figure out a way to cut down packet size to meet the receiver's MTU. So to prevent this problem, the network layer uses fragmentation. It takes the packet of 1400 bytes and divides it into two smaller packets of 700 bytes each. Now, the fragmented packets are sent to the destination and reassembled at the receiver's device to form the original packet. So this is called the fragmentation, breaking a packet into smaller pieces to meet the receiver's MTU. The most important protocol at the network layer is the Internet Protocol or IP. The IP protocol manages fragmentation, assigning IP addresses, etc. These are the protocols and devices present at the network layer. The router is the most important device at the network layer. It is the router that forwards the data packets to the destination. The data link layer receives data packets from the network layer, and the responsibilities of the data link layer include node-to-node data delivery, flow control, error control, physical addressing, framing, and media access control. So let's start with node-to-node delivery. Node-to-node data delivery means that the data link layer delivers data from one node to another. Now, what is a node? A node is a device that is part of a network and capable of forwarding and receiving data such as a phone, computers, servers, switch, router, modem, etc. Now let's understand node to node delivery in the context of the data link layer. If you recall from the network layer selects the route or path that data packets must go through to reach their destination, right? Let's say that network layer selects this route to deliver data from the source to a destination. Here we have 4 routers between the sender and receiver. The data must pass through these 4 routers to reach its destination. Now, these routers are also called nodes or hops. I will use the term nodes from this point forward because node is the terminology we use for routers in the data link layer. Now, if device A wants to send data to B, the data will not travel directly from A to B. Instead, it has to go through these nodes to reach the destination. The responsibility of the data link layer is to deliver data from one node to another or the next node that is on the way to the destination. When data leaves the sender's device, the data link layer delivers the data to the first node. Node 1 will then forward the data to node 2 and node 2 will further forward it to node 3. Eventually, the data will reach its destination. That's the node to node or hop to hop data delivery. Don't confuse node to node delivery with host to host delivery, which we have at the network layer. The network layer directly communicates with the receiver or destination device, and the data link layer takes care of the nodes or the next node that is on the way to the destination. Both layers at different levels take care of the data delivery from sender to receiver. Remember, when devices on the same network want to communicate with each other, they can directly communicate using the data link layer with the help of MAC addresses. The network layer is not required for sending data to each other within a single network. However, the network layer becomes essential when delivering data to devices located on different networks. Now let's discuss the flow control. We also have flow control at the transport layer, right? Flow control by definition serves the same purpose at the both layers. Flow control makes sure that the sender does not send more data than the receiver can handle or process. However, there is a minor difference. The transport layer directly controls the data flow between the sender and receiver devices. It ensures that the sender does not send more data than the receiver can process. Now, before data can reach the receiver's device, it must pass through nodes that are on the way to its destination, right? Therefore, we need a way to control the flow of data between these nodes as well. This is what the data link layer does. It controls the data flow between nodes. Flow control in the data link layer ensures that the sender node does not send more data than the receiving node can handle or process. It uses various algorithms to control the data flow, such as stop and wait. Again, the data link layer controls the flow of data between nodes, while the transport layer controls the flow of data between the sender and receiver. Now let's discuss error control. Just like the transport layer, the data link layer also checks the data for errors. However, there is a difference. The transport layer checks the data for errors when it reaches the destination device. But before the data reaches the actual destination, it goes through these hops or nodes, right? So similar to flow control, the data link layer checks for errors in the data at each node. I will explain in a minute why both layers check for errors. Error control in the data link layer is the process of detecting and correcting corrupted or lost data frames at each node. The data link layer uses a variety of techniques to detect and correct errors, such as parity check and cycle redundancy check. The most common types of errors that can occur at the data link layer include single bit errors, burst errors, and frame loss. The reason OSI model checks for errors at both transport and data link layer is simple. It improves the efficiency. Suppose there are no error checks at the data link layer or nodes. The data with errors reaches the destination device, and the receiver checks and detects errors. After detecting an error, the receiver requests the sender to resend the corrupted data. This is a time-consuming process because the receiver's request has to travel back through all the nodes along the path. However, detecting errors at a node before the data reaches the destination can fix them sooner. The node can request the sender to correct the error or resend the corrupted data. This saves time and improves efficiency. Now let's discuss physical addressing and framing. Physical addressing is the process of assigning MAC addresses to data packets. The data link layer assigns the MAC addresses of sender and receiver to each packet that it receives from the network layer to form frames. Data unit is called the frame at the data link layer. MAC address is also known as physical address. MAC address is a unique 12-digit hexadecimal number embedded into a computer's network card. A MAC address is permanently assigned to a network card and can't be changed. If two devices on the same network want to communicate with each other, they can communicate using their MAC addresses. Data exchange within the same network can be facilitated using MAC addresses without requiring network layer and IP addresses. As I mentioned, the data or PDU at the data link layer is called the frame. The data link layer converts packets into frames. It receives packets from the network layer and wraps them into frames. The data link layer properly formats data before it is sent to the physical layer. This process is called framing. Just like the network and transport layer, the data link layer also adds its own data or header to each packet that it receives from the network layer. The data link layer adds a header and a trailer to a data. Each frame contains a frame header, frame body, and a frame trailer. This is the structure of a frame. The header includes the MAC addresses of the sender and receiver devices as well as flow control information. The frame body contains the data or payload to be delivered to the destination. The packet that data link layer receives from the network layer is stored in the body or payload of the frame. It also adds a trailer at the end of each frame. Trailer includes error detection codes. We will get back to the frame structure in a dedicated video. There is more to frame than just these fields. Now let's move on to the media access control. Data link layer is divided into two sub-layers, logical link control and media access control. LLC handles protocols, synchronization, flow control, and error detection etc. Media access control manages data collisions. Let's understand what data collision is. Suppose devices are connected to a network through a shared cable, such as in bus topology, where devices connect and communicate with each other through a thick wire or cable. Now, in this type of network, things become problematic when multiple devices attempt to send data simultaneously. When multiple devices send data at the same time, the data can collide, which causes data loss. So in order to send data, each connected device has to access or use the shared cable when no other connected device is using it or sending data. Media access control makes sure that only one device sends data at a time to avoid data collision. Media access control makes sure that devices don't interfere with each other's data, which allows each computer to send and receive data without interference. Data is transmitted by a device only when the shared cable or link is idle and no one else is using it. The technology used for avoiding data collision is CSMA/CD. It stands for Carrier Sense Multiple Access Collision Detection. These are the protocols and devices at the data link layer. The network interface card is the most important device at the data link layer. Any device that deals with MAC addresses is a data link layer device. Another very important device at data link layer is the switch, which intelligently forwards packets based on the destination MAC address, ensuring efficient traffic flow within a network. Now the last or the first layer from the bottom is the physical layer. The data link layer prepares data to be sent over wires. It makes sure that the data is properly formatted so that it can be transmitted over the wires or physical mediums. The physical layer receives data from the data link layer and is responsible for transmitting data over physical mediums such as wires or wireless radio waves. The physical layer interacts with the hardwares that are used to send, receive, or carry data, such as cables, optical fibers, and radio waves. It is responsible for converting digital data into electrical or optical signals that can be transmitted over physical mediums. Before transmitting data to the actual physical infrastructure, the physical layer generates signals based on the medium that a device is using to connect to the network or access the internet. The physical layer receives data from the data link layer in the form of binary, zeros and ones. This is digital data or digital signals. However, ones and zeros can't be sent over transmission mediums such as cables or radio waves etc. The physical layer must convert digital data into signals that can be sent over the physical medium, which depends on the type of connection being used. For example, if you are connected to the network through Wi-Fi, then the digital signals are converted into radio signals or radio waves, and if you are connected through an Ethernet cable, the data is converted into electrical signals. This conversion is done by modem. After converting the data into the appropriate signals, the physical layer transmits the data over the physical medium from one node to another, and eventually data reaches at the destination. The data is called bits at the physical layer. How data is received and processed at the destination, it will be covered in the encapsulation and decapsulation video. These are the devices and protocols present at the physical layer. You might be wondering why hubs are physical layer devices while switches are data link layer devices. A switch can read MAC addresses and forward packets to the correct destination device based on that address. On the other hand, hubs can't read MAC addresses, so they forward every packet to all devices connected to them. Remember, anything that deals with MAC addresses is a data link layer device, and hubs are physical layer devices because they can't read MAC addresses. In this section, we will dive into the fundamentals of cryptography. Cryptography is a critical component of secure data communication in modern computing. It is absolutely necessary. You don't have to master it. However, understanding the fundamentals of cryptography is essential for everyone, especially for cybersecurity and network engineers. In this first video, we will explore what cryptography is and why it is important or required. So, what is cryptography? Cryptography, in simple terms, protects data. It allows devices to communicate securely over the internet. It protects data from cybercriminals, middlemen, or hackers. Let me first demonstrate data communication over the internet without cryptography. Then we will be able to understand why it is needed. Suppose device A and B want to communicate over the internet. A sends a hello message to B. Now, the data does not travel directly from the sender to receiver on the internet. Instead, it goes through various devices and networks to reach the destination. We don't know who can intercept the data as it travels to its destination. Now, what if a cybercriminal intercepts the communication? Then the hacker will be able to read all the details or data that the communicating devices exchange between them. Intercepting data is not that difficult. If you have basic hacking skills, you can intercept data easily. The problem becomes even more critical when users connect to important websites like banking portals, Gmail, or social media platforms. Interception of data communication with banks or other sensitive websites by hackers can have severe consequences and compromise your personal information. We have no control over who might intercept data because by design the internet is accessible to everyone. However, we can protect the data itself so that even if someone intercepts it, they can't understand the original message or information. The real problem here is the communication of data in plain text. Devices are sending and receiving data in plain text, so whoever intercepts it can easily read the original data being exchanged. Therefore, we needed a secure method for safeguarding and exchanging data. This is where cryptography steps in to address the problem. Cryptography encrypts the data before it is sent to the receiver. After encrypting, the data becomes unreadable like this. the hello message gets scrambled into this unreadable encrypted text. Now this encrypted message is then sent to the destination. Now even if cybercriminals intercept the data, they will not be able to read the original data. All they will see is the encrypted data. The data is decrypted or converted back to its original form only at the destination. This is the magic of cryptography. Only the receiver can decrypt data back to its original form. So that's how cryptography protects data and ensures it is delivered securely to its destination. This is a basic technical overview of cryptography. We will dive into more details in the upcoming videos. So let's start with encryption. Encryption is the process of transforming plain text or readable data into unreadable data to secure it from unauthorized access. Let's say the sender wants to send a hello message to the receiver. Now before sending the message to the destination, encryption scrambles or encrypts the message into unreadable random characters like this, so that only the authorized or intended receiver can read it. Data is encrypted in a way that only the intended receiver can read the original message. This encrypted data is then transmitted to its destination. Now, if hackers hack or intercept the data, they will not be able to read the original message. Attackers will still be able to access or view the data, but all they will see is the encrypted message, not the original data. Now, decryption is the opposite of encryption. Once data is encrypted, it is sent to the destination, and at the destination the encrypted data needs to be decrypted so the receiver can read the original message. Now the process of converting encrypted data back to its original form is called decryption. Remember, only authorized users can decrypt the data. Data is always decrypted at the destination. Now let's discuss the difference between encryption and cryptography. Cryptography is a broad term that includes everything related to data security. Encryption is essentially a component or part of cryptography. Cryptography, on the other hand, covers everything related to data security, including encryption and decryption, along with all the necessary steps involved in the data security process. So cryptography is a comprehensive term that includes everything related to encryption and decryption. Both are integral parts of cryptography. When it comes to encryption, there are two primary types, symmetric and asymmetric encryption. In this video, we will focus specifically on symmetric encryption and how it works. Now, symmetric encryption is also known as symmetric key encryption. It uses a single key to encrypt and decrypt data. The word symmetric means the same. Therefore, symmetric key encryption uses the same key to both encrypt and decrypt data. This key is also known as the secret key. The concept of the key in symmetric encryption is very similar to a door key. We use the same key to both lock and unlock the door, right? Only the key that locks the door can unlock it. The same principle applies to symmetric key encryption. The same key is used for both encrypting and decrypting data, and no other key can perform these functions. The data is encrypted using complex encryption algorithms. An encryption algorithm is essentially a technique or a set of steps used for scrambling or encrypting data. There are many encryption algorithms used in symmetric encryption, such as AES, DES, Blowfish, etc. to encrypt data in real-world applications. Now I will explain symmetric key encryption using the simplest and oldest encryption algorithm. This will help us easily understand the process and how an encryption algorithm and a key work together to encrypt and decrypt data. Encryption is not a new concept. It has been used for centuries to protect information even before computers and digital data existed. The first known data encryption method was used by Roman King Julius Caesar. The technique or encryption is also known as Caesar cipher. The Caesar cipher is one of the simplest and oldest encryption methods, named after Julius Caesar, who used it to protect his military messages such as when to attack, retreat, etc. Caesar cipher serves as a foundation for understanding the concept of symmetric key-based encryption. Now let's understand symmetric key encryption using the Caesar cipher. Let's say that device A wants to send the message hello to device B securely. As I mentioned at the beginning, the message is encrypted using a secret key in symmetric encryption. Let's say the secret key is 2. Now, the encryption algorithm or Caesar cipher works by shifting letters forward by a fixed number of positions. In this case, we are using 2 as a shift value, so it will move each letter 2 positions forward. Caesar cipher is also known as Caesar shift or shift cipher. The algorithm specifies shifting or moving letters forward by the secret key value for encrypting data. In my case, the secret key is 2, so we will move each letter forward by 2 positions. So if you move H 2 positions forward, it becomes J, E becomes G, LL becomes NN, and O becomes Q. So this is the encrypted data or text. Hello has been encrypted into this. Now remember, this is very important. This encrypted text or message is known as the ciphertext in cryptography. Ciphertext is basically the encrypted message or data. Now, after encrypting the data, A sends the ciphertext to the destination. The receiver uses the same secret key, which is 2, to decrypt the data to its original form by reversing the process. The encryption algorithm involves shifting each letter 2 positions forward in the alphabet to encrypt data, right? Now, to decrypt the message, the algorithm reverses this process by shifting each letter 2 positions backward. For example, the J becomes H and the letter G becomes E, the letters NN becomes LL, and Q becomes O. Now we have successfully restored or decrypted the ciphertext to its original form hello. This process is known as decryption. So that's how the algorithm and key work together. The algorithm specifies the shifting of letters by the shift value, while the shift value itself is the secret key. Now, if A wants to communicate with other device, it generates a unique secret key for each connection. Computers or devices in the real world don't use or rely on simple encryption methods like the Caesar cipher to encrypt data, because the Caesar cipher can be decrypted very easily. The Caesar cipher method is a valuable tool for explaining the concept of symmetric key-based encryption. The encryption algorithms utilized by computers involve highly complex mathematical equations. Encryption algorithms that computers use, such as AES and Blowfish, use sophisticated mathematical calculations to encrypt data. AES is the current industry standard and is highly secure. It is used for securing communication. Now let's address the very important question: how does the receiver know or obtain the secret key? As we discussed earlier, both the sender and receiver need the same secret key to encrypt and decrypt data, right? If the sender uses 2 as the secret key to encrypt data, then the receiver needs the same key to decrypt the data. This means we somehow need to share the secret key with the receiver so it can decrypt the data using the same key that encrypted it. However, sending the secret key directly to the receiver is not safe. Let's say if the sender sends the secret key directly along with the data to the receiver, then hackers can intercept both the secret key and the ciphertext. Consequently, they can easily decrypt the message using the secret key. That's why the key is not sent directly from sender to receiver. Instead, the key is exchanged or established securely using the Diffie-Hellman protocol. The Diffie-Hellman protocol uses complex mathematical equations that allow both the sender and receiver to independently establish the same secret key without directly sharing it. So Diffie-Hellman essentially helps both the sender and receiver establish the same secret key without directly exchanging it. Remember, the secret key is always established before both the sender and receiver start exchanging actual data. After establishing the key, both devices then begin exchanging data securely. It is a proven method for key exchange and is considered extremely difficult for a third party to intercept or predict the key. That's it for this video, guys. Let me know if you come up with questions. Before we dive into the specifics of asymmetric encryption, let's first understand why it was developed. Asymmetric encryption was developed to address the limitations of symmetric encryption. As we discussed in the previous video, symmetric encryption requires the sender and receiver to share a secret key before secure communication can begin. The key exchange is typically secure, but there is always a potential risk of compromise. Both symmetric and asymmetric encryptions have their distinct applications and uses. Asymmetric encryption solves the key sharing problem of symmetric encryption. Asymmetric key encryption is also known as public encryption because it uses two separate keys to encrypt and decrypt data: the public key and the private key. The public key is typically used to encrypt the data and the private key is used to decrypt it. The public key, as the name suggests, is either publicly available or shared with authorized recipients or receivers. The corresponding private key is kept private and is not shared with anyone. Now let's understand the essential fundamental terms of asymmetric encryption before diving into how it works. Let's say A wants to send hello to device B. Now, before exchanging the data, both devices will generate two keys each: the public key and the private key. The public and private keys of each device work together because they are always mathematically related or linked together. Remember this point, it is very important in asymmetric encryption. Suppose if device A encrypts its data with its public key, then that data can only be decrypted using its private key. No other key can decrypt it. Similarly, if A encrypts data using its private key, then the data can only be decrypted using its public key. As I mentioned earlier, both keys are mathematically linked together. So if you encrypt data with one key, then only its corresponding key can decrypt that data. The same applies to B and all other devices that use asymmetric encryption. If B encrypts data using its public key, then only its own private key can decrypt the data and vice versa. In the real world, the public key is always used to encrypt data and the private key is used to decrypt it. Therefore, the public key is shared with other devices. Now let's see how the entire communication is securely carried out using asymmetric encryption. Suppose A wants to send the hello message securely to B using asymmetric encryption. The first step in asymmetric encryption is that both the sender and receiver generate two keys each, a public key and a private key. Now, after generating keys, both A and B will exchange their public keys. A will send its public key to B and B will send its public key to A. After receiving the public key of B, A will use public key of B to encrypt its data. The hello message will be converted into ciphertext after encryption. Now, the encrypted data or ciphertext is sent to B. Now, how does B decrypt the data? B has two keys, its own private key and the public key of A, right? Remember, the data B received was encrypted using its public key, which it sent to A. Now, only the private key of B can decrypt the data because it's the only key mathematically linked to it. B already has that private key. It shared its public key and kept the private key. So obviously B decrypts the data using its private key because the data that A sent was encrypted using its public key. So the private key of B will decrypt the data back to its original form, hello. The public key can't because it is not mathematically linked to the key that encrypted the data. So basically B says to A, take my public key, then encrypt the data that you want to send to me with it and then send it to me so I can decrypt it using my private key. Similarly, if device B wants to send data to device A, it will use the public key of device A to encrypt the data. Upon receiving the data, device A will use its own private key to decrypt it. So to summarize, in asymmetric encryption, both the sender and receiver exchange their public keys before exchanging data. So the sender can encrypt the data using the public key and then corresponding private key is used for decryption. That's why asymmetric encryption is considered more secure compared to symmetric encryption because you never need to share the private key that decrypts the data. The algorithm that powers asymmetric encryption is RSA. RSA encryption is an asymmetric encryption algorithm named after its three inventors, Rivest, Shamir, and Edelman. Asymmetric encryption uses RSA to securely exchange data over the internet. In this section, we will learn about hashing. This is the first video on hashing, and in this video, we will understand what hashing is and why it is needed. Similar to symmetric and asymmetric encryptions, hashing protects data. Hashing is also a fundamental part of cryptography. However, hashing is slightly different from encryption. So let's first understand what hashing is. In cryptography, hashing is a technique that takes a data or a message as input and generates a fixed size output. It takes any given input and transforms it into a random fixed value output, representing the data in a condensed form. I know it sounds confusing and overwhelming right now, but don't worry, I will explain how it works in the next video. Everything will become clear once you learn its working. So there is no need to feel lost at this point. For now, the important thing is to understand the problems that hashing solves and why it was developed. Hashing addresses two major problems: data integrity, storing and verifying passwords securely. Let's first discuss the important part, data integrity, where hashing plays a crucial role. Data integrity means that the receiver receives error-free and unaltered data. Hashing ensures that data remains unaltered or unchanged during transmission or storage. Let's say device A wants to send a file to B. Now, if a cybercriminal intercepts the file and modifies the file contents, then sends the modified file to the intended receiver, it compromises the file's integrity. The receiver will not be able to determine whether they received the original or modified file. Therefore, we need a mechanism to check the integrity of files or data. This is precisely the problem that hashing addresses. It ensures that original, valid, and unaltered data reaches the intended destination by detecting any changes or modifications that may have taken place during transmission. Another crucial application of hashing is securely verifying and storing passwords. Web and other applications rely heavily on hashing for secure data storage, particularly passwords. Hashing essentially provides an additional layer of protection. This will be discussed in a dedicated video later in the section. Beyond these crucial applications, hashing has a wide range of other use cases in cryptography, such as digital signatures, secure key derivation, random number generation, etc. In this video, we have a lot to cover. We will start by exploring the fundamentals of hashing, how it works, how it protects the integrity of files or data, and what a collision is. Hashing is a complex mathematical process that takes an input of any size and produces a fixed size output called hash value. Here is how hashing works. We provide input or data to a hashing function. Hashing functions are responsible for generating hashes. The input can be anything: a single letter, word, a paragraph, a text file, PDF file, or any other data. Regardless of the input's size, the hashing function always produces a fixed length output. For the sake of simplicity, let's assume that we have a hashing function specifically designed to generate a fixed length output of 10 random characters. This means that regardless of the input you provide to this function, it will always produce an output with a fixed length of 10 unique random characters. So if your input is a single character such as B, this hashing function will produce a 10 character random string like this as its output. Now let's increase the input size. Suppose the input is the word hello. The output will be different, such as this. However, the output length will always be a fixed 10 character long random string. Even though the input size has increased, the hash will always produce a fixed length output of 10 characters. Similarly, if you provide a file as input, the function will still produce a 10 character long output. Now, in the real world also, hash functions consistently produce fixed length outputs regardless of the length of the input. This applies to all types of data and files, including large files with sizes in gigabytes. The functions will still generate a fixed size output. That's the fundamental nature of hashing functions. There are numerous hashing functions used in various real-world applications such as MD5, SHA-1, SHA-2 and SHA-256. All of these functions produce a fixed size output. However, the exact output size varies depending on the specific hash function being used. We will discuss them in more detail in the upcoming videos practically. For now, let's dive more closely into the inner workings of hashing. To illustrate the hashing process in a clear and understandable way, I will use a very simple hashing function as an example. This hashing function works by taking the position of each letter and then adding them together to generate the hash. So here we have letters along with their numerical positions. Let's say I want to generate hash for the hello message. The letter H is at the 8th position, so I will take the value 8. E is at the 5th position. L is at the 12th position. Since there are two L's, it is 12 again. O is at the 15th position. So if we add all these numbers, we get 52. Now the result or output that a hash function produces is called a message digest. The message digest is also known as a checksum, digital fingerprint, or simply hash value. Now, the 52 is basically the hash value or fingerprint of the word hello. So this 52 essentially represents this message. As I mentioned in the previous video, hashing is used to ensure data integrity. It guarantees that data remains unmodified when transmitted from sender to receiver. Here is how it works. When data or a file is sent from one device to another, a hash value is also transmitted alongside it. Suppose device A sends the hello message to device B. It will also send the hash value calculated for hello, which is 52. Now, when hello reaches B, the receiver also calculates the hash value of hello independently using the same function that was used to calculate the hash by the sender. Now, after calculating hash, it gets 52. Now, it compares the hash value that it calculated to the value sent by the sender. If the hash value the receiver receives matches its own calculated hash value, then it means the file or message was not modified. It received the correct message. Now let's say before the message reaches the actual receiver, a hacker intercepts it, modifies hello to hell, and then sends this modified message to the receiver. Now the receiver calculates the hash. This time it will be 37. The hash value for hell is 37. When the receiver compares this new hash value with the hash sent by the sender, it will not match. This is because the message has been modified, resulting in a different hash. If the modification is detected, then the message gets dropped or discarded. Remember, even a minor change produces a different hash value, which helps to detect changes in a file or data. In the real world, you may have noticed that when you download files from reputable websites, they often provide a hash value alongside the file itself. This hash is typically displayed on the website or included in a separate file. After downloading the file, you are encouraged to calculate the hash of the downloaded file using the same hash function that the website or application used to generate the original hash. If the hash you calculate matches the hash provided with the file, it is a strong indication that you have downloaded the correct file without any corruption or tampering. So guys, that's how hashing works and ensures the data integrity. Obviously, this is the simplest possible hash function. Such simple functions are not used in real-world applications. This was just for explanation purposes. This function is very weak, predictable, and easy to crack. In the real world, hash functions such as SHA-1, SHA-56 use very complex mathematical calculations to produce a hash or message digest. Data is put through a complex process to produce a hash. Now, there are several criteria that a hash function must meet to be considered secure and reliable for real-world use. Let's take example of our simple hashing function. This function produces 52 hash value for the word hello, right? Now, there are many words that can add up to 52. For example, two Z's can also produce a hash value of 52, and the word zebra also adds up to 52 along with many other combinations. This is called collision. A collision in hashing occurs when two different pieces of data or message generate the same hash value using the same hash function. This hashing function is also producing the same hash values for different messages. This is bad. If two different pieces of data have the same hash value or generate the same hash, comparing their hashes will not tell us which one is the original. This can lead to falsely accepting corrupted data as valid, potentially causing major issues. So this function is obviously not suitable for real-world applications because it is not secure, is easily predictable, and easy to crack. Therefore, a hash function must always produce a unique hash value or output for every distinct or individual input. This is the first and most crucial criteria. Another very strict requirement for a hashing function is that it must always produce a fixed length of output. My simple hash function will not produce a two-digit output or hash value if I provide a line or paragraph as an input. The output will be 3 digits or more. But in real world, a hash function always produces output of a fixed length, no matter how long or small the input is. It must always produce a fixed length output. So guys, to summarize, a hash function must produce a unique output for every distinct input, and every output must be of a fixed size. Command. Ping is one of the most commonly used commands in Linux networking. It is pre-installed on all three major operating systems, Windows, Mac OS, and Linux. Ping is a simple yet very important command. It is a network connectivity tool used to check network connectivity and troubleshoot issues. Let's say you are experiencing problems related to your internet connection. In such situations, you can use ping command to determine whether your internet connection is working or not. Ping can also be used to check websites. If you are having trouble accessing a website, you can use ping to verify whether the website or server is up and running. Now let's jump into the practicals. Type ping space and we need to provide an IP address or a domain name to the ping command. So let me specify, let's say google.com. The way ping command works is it essentially sends ICMP packets to the specified host or destination and then waits for a response from the specified host. Let me press enter. By default, the ping command keeps running forever. You have to stop it manually. So to stop the ping command, press Ctrl plus C together, and at the bottom we have the statistics for the connection. 14 packets transmitted. It means my system sent 14 packets to the google.com and 14 received. It means all the packets that ping sent to the Google responded to all those 14 packets. Now it proves two things. One, my internet connection is working, because in order to send packets out on the internet, you need to have a working internet connection. It also proves that Google is up and running because it responded to the packets which were sent by ping. So both systems communicated successfully over the internet. Now, as we saw, the default ping command sends unlimited packets. Now let's do some customization. I only want to send a limited number of packets. So type ping -c 5 google.com. This time ping is only going to send 5 packets or whatever number you specify after the -c parameter. So let me press enter. As you can see, it sent 5 packets and received all those 5 packets. So guys, that's how you can check your internet connectivity. If your system is able to send packets out in the internet, it means that your internet connection is working just fine. And of course, if it receives packets from the host that you provide to ping command, it also means that the host that you are connecting to is also up and running. Now, if your internet connection is not working, then you will see messages or error messages like this: temporary failure in the name resolution. Remember, this message can also appear if you provide a wrong host name or domain name that doesn't exist. This is the typical error message when your internet is not working. Now let's say if the host that you are connecting is not up and running, then in the statistics section you will see something like 0 packets received. It means that the host is not up and running. Or there could be another reason. Maybe the host that you are connecting to or pinging to has blocked the ICMP packets. The common response, if host is not up and running or is down, you will see the 0 packets received. In this section, we will get started with the binary number system. In this particular video, we will learn what a number system is and the types of number systems used by computers. If you are a complete beginner, the binary number system might seem scary or intimidating, but don't worry, everything has been simplified for you. Just pay attention. Before we get into the binary number system, let me explain what a number system is in general to set the context and groundwork for understanding the binary number system. Some of you might find this too basic. I believe it is important to cover the absolute fundamentals to ensure everyone, including complete beginners, feels comfortable and well equipped to learn. A number system is a way of representing numbers using specific symbols or digits such as 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. We use these digits to represent or write all the different numbers we can think of, right? Now, there are several number systems that are specifically used by computer systems, including decimal, binary, octal and hexadecimal. Let's start with the number system we are all familiar and comfortable with, which is the decimal number system. The decimal is a base 10 system. So what is base first? Base in this context refers to the total number of digits used to represent numbers. Base 10 therefore means the decimal number system uses 10 digits from 0 to 9 to represent numbers. The 10 digits that decimal uses are 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. 0 is also counted. So from 0 to 9 there are 10 digits that decimal system uses. We can represent or write any numbers using these 10 digits, such as 6, 7, 23, 100,000, or any number that you can think of. All numbers are represented using combinations of these 10 digits. We use the decimal number system in our daily lives to count things, right? And it works pretty well for us humans. Now, computers use the decimal number system for displaying information in a human readable format. When you see any information that contains numbers, it is the decimal number system in use. Now let's move to the main part of the video, the binary number system. The binary number system is a base 2 system, meaning it uses only 2 digits to represent numbers. Those digits are 0 and 1. The decimal system uses 10 digits from 0 to 9 to represent numbers. On the other hand, the binary system only needs 2 digits, 0 and 1. With these 2 digits, we can represent or write any number through combinations of 0 and 1. In upcoming videos, we will learn how to convert any decimal number into its binary equivalent. Now, the binary number system is used by computers and all digital devices. You may have heard that computers only understand binary, right? Binary is basically the language of computers. Now, what does it actually mean when we say computers only understand binary? Data is stored, transmitted, and processed only in binary by computers. Everything stored in computers, from characters, audio to video files, and images, is represented using binary. This means everything ultimately gets converted into combinations of zeros and ones. For example, when you save an image on your computer, it is first translated or converted into binary before being stored in the system. Similarly, all types of data are converted into binary before being stored or processed. When a computer performs any task or calculation, the data is first converted into binary, then it is processed. In short, everything is represented by combinations of just 2 digits, 1 and 0. Computers use only binary numbers for processing and storing data. Now, the binary number system is very important in networking, specifically for topics like IP addressing, CIDR notation, network masks, subnetting, etc. We need to understand how to convert decimal to binary and binary to decimal when working with IPv4 addressing. Then we have the octal number system. Octal is a base 8 system. There are a total of 8 digits that can be used in octal: 0, 1, 2, 3, 4, 5, 6, and 7. These 8 digits are used to represent numbers. However, octal is no longer as widely used in computing as it was in early computing. The next number system is hexadecimal. In the next video, we will cover hexadecimal in detail because it deserves a dedicated video. Let's begin by understanding what hexadecimal is. We don't need to learn the in-depth workings of hexadecimal. We only need to know its uses, where it is used, and why it is preferred in certain situations. That is sufficient. Hexadecimal is a combination of 2 words, hexa and decimal. Hexa is a Latin word that means 6, and decimal, as we know, is a base 10 number system, right? So if you add up hexa, which is 6, and decimal, which is a base 10, we get 16. Therefore, hexadecimal is a base 16 number system. Hexadecimal uses 16 digits to represent numbers or data. These digits are 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. These are decimal numbers, right? Now the remaining 6 are letters A, B, C, D, E, F. So we have all the decimal numbers in hexadecimal plus 6 letters. Now A represent 10 in the hexadecimal system, B represents 11, C represents 12, D represents 13, E represents 14. So hexadecimal uses these 16 digits to represent numbers and other data. Now let's discuss the actual question. What are the use cases of hexadecimal numbers and where do they fit in? Hexadecimal numbers have a wide range of applications. The hexadecimal number system represents binary and decimal data in a more concise and readable format. Let's understand the real-world use of hexadecimal with MAC addresses. So now what I'm gonna do is open my command prompt and show you the MAC address, what it looks like. So press Windows key, type cmd, click on command prompt, type IP config / all, press enter, and under the wireless LAN adapter Wi-Fi, locate the field physical address. Now this is the MAC address. As you can see, it is in hexadecimal digits. A MAC address is always represented using hexadecimal digits. A MAC address is a 12 hexadecimal digits long, which means it has 6 pairs of 2 hexadecimal digits, right, as you can see here. Now if the same MAC address were represented using the decimal number system, we would need more than 12 digits, probably around 18 digits to represent a MAC address. The hexadecimal system precisely represents data in fewer digits compared to hexadecimal. Hexadecimal numbers are also commonly used in memory addressing, data compression, and even color codes. You have likely seen codes that look like this. These codes use hexadecimal system. If you are a web developer, you must have used color codes, right? Color codes are written in hexadecimal because they can compactly represent the color codes. Understanding binary to decimal conversion and vice versa is crucial for working with IP addressing, subnetting, and other related topics. It may sound challenging, but it is actually simple. There are several methods for converting decimal to binary, but I will show you the simplest one. Now I want to convert this binary number 00101011 into decimal. The binary is a base 2 number system, which means it uses only 2 digits 0 and 1 to represent numbers. Each digit's value increases by a factor of 2 or doubles as you move leftward in the number. Now let's get down to the real work without complicating it. So let me write the binary number that I want to convert into decimal, which is this. It is an 8-bit number. Now to convert, underneath the rightmost digit, write 1, start with 1, and as you move to the left, multiply the number by 2. 1 multiplied by 2 is 2. 2 multiplied by 2 is 4. 4 into 2 is 8. 8 into 2 is 16. 16 multiplied by 2 is 32. 32 into 2 is 64. 64 multiplied by 2 is 128. Keep multiplying the previous number by 2 until you reach the leftmost binary digit. Since we are dealing with only 8 binary digits, the multiplying or doubling stops there. There is no need to continue beyond the last bit. We now have the place value for each binary digit. If there were another binary digit, we would need to multiply by 2 again to get its place value, which would be 256. Since we are working with an 8-bit binary number, we don't need another value. Now we have everything needed to convert this binary number to a decimal number. To convert binary number to decimal, first identify the binary digits where there is a 1. We have a total of 4 ones. Now mark or circle all the place values where there is a 1 in the binary number. Essentially, circle all the decimal values that correspond to the ones. After marking the place values that correspond to ones, add up the marked values. This will give you the decimal equivalent of the binary number. This is as simple as that. The method is simple. If a binary digit is 1, its corresponding decimal value is included in the final sum, and if the binary digit is 0, its value is not added to the sum. Let's add these marked values or numbers that are underneath the ones. So 32 plus 8 plus 2 plus 1 is 43. So decimal equivalent of this binary is 43. So this is as simple as that. Now let's look at one more example for clarity. We will once again convert an 8-bit binary number to decimal. The reason for specifically working with 8 digits is that we commonly deal with 8-bit numbers in IPv4 addressing, subnet masks, subnetting, and related topics. Most of the time we need to convert 8-bit binary to decimal and decimal to binary. Let's say we have a given 8-bit number 100101110. The method for conversion remains the same. Underneath the rightmost digit, start with 1. As you move to the left, multiply the number by 2. 1 multiplied by 2 is 2. 2 into 2 is 4. 4 multiplied by 2 is 8. 8 multiplied by 2 is 16. Then 32 multiplied by 2 is 64, and 64 into 2 is 128. Now we have the place value for each binary digit. Now circle the decimal numbers underneath the ones. 128, 16, 4 and 2. Now adding them together we get 150. Therefore the decimal equivalent of this binary number is 150. In this way, you can convert any 8-bit binary number into a decimal. And of course, if you are given a longer binary number, then add the place values by multiplying the previous value by 2. We can also do quick mental calculations. Just memorize the place value of each digit and add them where the digit is 1. With practice, it can be achieved easily. So that's all you need to know when it comes to binary to decimal conversion for IPv4 addressing. We are continuing where we left off in the previous video. In this video, we will learn how to convert any decimal number to binary. Let's say we have a decimal number 59 and we want to convert it into a binary. The process is similar to the binary to a decimal conversion. This time, to convert the decimal number to binary, we first need to start by writing out the place values starting from the leftmost digit. Write 1 in the ones place and then multiply each subsequent place value by 2 as we move left. 1 multiplied by 2 is 2. 2 times 2 equals 4. 4 multiplied by 2 is 8. 8 into 2 is 16. 16 into 2 is 32. 32 times 2 equals 64, and 64 times 2 equals 128. These 8 consecutive powers of 2 provide enough place values to represent any decimal number less than 256. Now to convert 59, we need to find the binary digits or bits that we can add up to create the number 59. The process is straightforward. We identify numbers that can be used to reach the target number without exceeding it. We start with the largest number, which is 128 in our case. Since 128 is greater than 59, we can't use it to get or reach 59. If we can't use a number, we put a 0 under it. If it is used, then we write 1. So 0 here. The same goes for 64. It is greater than 59. So we can't use it. Again, put 0 under it. Now we have 32. Yes, 32 can be used to reach 59. So put 1 under that number. Next is 16. Can it also be used? The answer is yes, since 32 plus 16 is 48, which is less than 59. We can use it. So put a 1 under 16. Remember, if adding a number exceeds our target, we have to write 0, and we use 1 when a number can be used to reach the target without going over. Next is 8. Can we use 8? Yes, we can. 48 plus 8 is 56. So put 1 under 8. Then we have 4. Can we use 4? No, we can't. Adding 4 to 56 would result in 60, which exceeds our target number 59. So put a 0 in the corresponding position. Moving on to 2. Can we use it? Yes. 56 plus 2 is 58. So put 1 under 2. Then we have 1. Can we use it? Yes. 58 plus 1 is 59. Therefore, we place a 1 in the 1 position. So this is the binary representation of 59. 0, 0, 1, 1, 1, 0, 1, 1. So guys, this way you can convert any number from decimal to binary. Now let's convert one more decimal to binary. Let's say 171. The process is the same. We need to identify numbers that can be used to reach the target number without exceeding it. Again, we start with the largest number, which is 128. Since 128 is less than 171, we can use it to reach 171. Therefore, the write a 1 in the corresponding position. Next is 64. Adding it to 128 would exceed our target. So we skip it and write a 0 in its position or beneath it. Moving on to 32. Adding it to 128 gives us 160, which is still less than 171. Therefore, we use 32 and write a 1 in its position. Next number is 16. Adding it to 160 results in 176, exceeding our target number 171. So we skip it and write a 0 in its position. Next is 8. Yes, 8 can be used to reach 171. 160 plus 8 is 168. So we write 1 under it. Next is 2. Yes, 2 can also be used to reach 171. 168 plus 2 is 170. So we use it and we write 1 under it. Finally, 1 is all we need to reach 171. Therefore, we write 1 in its position. 170 plus 1 is 171. So 10101011 is the binary equivalent of decimal 171. Now this is an 8-digit number. So highest number an 8-bit binary number can represent is 255. If you add all the digits together, you get all possible combinations from 0 to 255. Therefore, these 8 bits can represent numbers from 0 to 255. If you need to represent a number larger than 255, you will need more than 8 bits. All we need to do is increase the number of bits. For example, adding just one more bit or 9th bit allows us to represent numbers from 0 to 511. You can simply add bits as needed to handle larger numbers. I specifically used 8 bits because 8-bit binary conversion is heavily used in subnet masks and subnetting. Each part in an IP address or subnet mask uses 8 bits called an octet. Therefore, for these applications, understanding 8-bit conversion is sufficient and you don't need to dive into advanced algebra. It is more than enough. In this video, we will learn about two operators, the OR operator and the AND operator. Both of these operators are also known as logical operators. Specifically, the AND operator plays an important role in IPv4 addressing, especially for tasks like identifying network IDs, subnetting, and related topics. Understanding AND operator is essential for mastering IPv4 addressing, but don't worry, it is actually quite simple to grasp. So let's start with AND operator. The AND operator is a Boolean logical operator used in algebra and computer science. It only accepts Boolean values as inputs, meaning you can't provide decimal numbers as inputs. Now there are only two Boolean values, true and false. The AND operator accepts only these two Boolean values as inputs, and the result of an AND operation is always either true or false. It is important to remember that the Boolean value true is commonly represented by 1 and false is represented by 0 in computer science. This means you can use 1 instead of true and 0 instead of false in most cases. Now let's understand how the AND operator works. We need to provide two Boolean values or inputs to the AND operator. Then it gives an output that is either true or false. Here I have three columns, input 1 and 2. The AND operator requires two inputs or Boolean values. Then the third column is going to display the output or result of the AND operation. Now I have enclosed 1 and 0 in brackets because true and 1 are equivalent in Boolean logic, and 0 and false are also synonymous or same, so don't get confused here. The first expression is true and false, or 1 and 0. It evaluates to false. The result is false. Then we have false and true. The result is also false. The false and true also evaluates to false. Now we have the last combination, true and true, or 1 and 1. Now if we apply the AND operator to these two true values, the output will be true. So the only time the result of the AND operation is true when both values or inputs are true. So remember this important point. Only true and true result in true in AND operator. All other combinations result in false. So that's all about AND operator. With two Boolean values, you can only have 4 possible combinations of inputs: true and true, true and false, false and true, and false and false. Now let's talk about the logical OR operator. While not as important for IPv4 addressing as the AND operator, understanding it is still crucial. In some ways, it functions similarly to AND operator. Once again, I have 3 columns, input A, B, and the result. This time we will be using OR operator. Unlike AND, which produces a true result only if both inputs are true, the OR operator produces a false result only when both inputs are false. The first expression that we have, true or false, or 0 or 0. The result is true because at least one of the operands is true. Now false or true is also true, and true or true is also evaluated as true. However, the OR operator produces a false output only when both inputs are false. This means that if one operand or input is true, the result is always true. This is the important distinction between the OR and AND operators. All other combinations of inputs will result in a true output except for false and false. So to summarize, AND operator produces true in its output when both inputs or operands are true, and the OR operator produces false as its output only when both inputs are false. That's all you need to know about these two operators.